Good morning, everyone. Yeah, very good morning. Shall we begin the session? In the last class, we have finished with the topic that is a rename operation. Yes, let's start with the revision of the previous class, what we have covered. In the last class, we have studied about how to rename, or it will be very useful to able to give them names for the algebra operations that is referred, that is done by the rename operator, and that is denoted by the lowercase Greek letter rho. Let's do this. Given a relational expression that is given with the e, and take out the values that is available with the expression that is available denoted by the lowercase letters p. Now, this given a relational algebra, that an expression that returns the expression e under the name x. So a relation R by itself is considered a trivial relational algebra expression. Therefore, we can also apply the rename operation to a relation R to get the same relation under a new name. Then a second form of the rename operation is as follows. Assume that a relational algebra expression E has a artery n, then the expression P(A)xy(E) returns the result of the expression E that takes the value under the name x with the attributes renamed to the A1, A2, An. And to illustrate the renaming a relation, we consider the query, find the highest salary in the university. Our strategy is to find first a temporary relation that consisting of the salary then that are not the largest, and take out the set difference between the relation pi salary instructor and the temporary relation just computed to obtain the result. Then in step number 1 we take the two computation, that is the instructor and the instructor, both the tables, by using the Cartesian product and forming a selection to compare the value of any two salaries appearing in one tuple. And firstly, we need to devise a mechanism to distinguish between the two salary attributes. So we shall use the rename operation to rename one reference to the instructor relation. Therefore, we can reference the relation twice without ambiguity. This is the salary 65, 90, 40, 60, 87, 75, 62, 72, 80, 92. Then it is used with the pi, instructor salary, sigma, instructor dot salary, t dot salary, instructor, pd, instructor. So these are given with the result of the expression that is that we can use to write the temporary relation that consists of the salary that are not the largest. This is the pi, instructor dot salary, d dot salary, instructor, pd, instructor. This expression gives those salary in the instructor relation for which a larger salary appears somewhere in the instructor relation, that is named as a or renamed as a d, and the result contains all the salaries except the largest one. So then step number 2 is the query to find out the largest salary in the university can be written as pi salary instructor, pi instructor dot salary, d dot salary, instructor, pd, instructor. This rename operation is not strictly required, and it is possible to use a positional notation for the attribute. So we can use, or we can name the attributes of a relation implicitly by using the positional expression, by using the positional notation, where $1, $2 refers to the first attribute, second attribute, and so on. Therefore, the positional notation also applies to the results of the relational algebra operations. And the following relational algebra expression illustrates, that is a use of the positional notation that uses the expression that we saw earlier also, that computes the various salaries that been not the largest. So this is a pi as for $4, $4 is less than $8, then instructor and the instructor. So note that the Cartesian product concatenate the attributes of two relations that is used with the result of the Cartesian product. And a positional notation can also be applied to refers to as a relation names if a binary operation need to distinguish between the two operand relations. For example, if I'm talking about the $R1, that could refers to the first operand relation, $R2 that could also refer to the second operand relation of a Cartesian product. In this case, the positional notation is inconvenient for the human since the position of attribute is a number rather than an easy to remember attribute name. Hence, we do not use a positional notation in the text box. The next one is the formal definition of the relational algebra. So whatever the operation that allows to give a complete definition of an expression in the relational algebra, and the basic expression that consists of either one of the following, that is a relation in the database, then constant relation that is written by listing its tuple within the braces. That is the curly braces. For example, 222, 5 times 2, instant physics 95,000, 76543 sync finance 80,000. Then a generic expression in the relational algebra is constructed out of the smallest sub-expression, and let E and the even be the relational algebra expression. Then the following are the relational algebra expression that is used: even union E2, even minus E2, even into E2, where P is a predicate on the attributes in even, and pi s is a list consisting of a set of the or some of the attributes, where x is a name for the result given in the even. Then the additional relational algebra operation, that is a fundamental operation of the relational algebra that is given, that are sufficient to express any relational algebra query. For example, yeah, it is restricting ourselves to just the fundamental operations. So there are certain common queries that are lengthy to express. Therefore, we define additional operations that do not add any power to the algebra, but simplify common queries. For each new operation, we give an equivalent expression that uses only the fundamental operations. The next is the set intersection operation. So we shall define a set intersection, that is reverse of U, and suppose we want to find the set of all the courses taught in both the fall 2009 and spring 2010 semester. So using the set intersection, we can write by course ID sigma semester equals to 4. That means we are fetching the course ID column, and what is a tuple that we are going to select, that is what is condition. Condition is semester equals to 4 and the year is 2009 from the section table. Then intersection with the pi, course ID, semester spring, year 2010. Then again from the section table. The next one is a natural join operation that is also used with the Cartesian product, that includes a selection operation on the result of the Cartesian product, that most often requires with all the attributes that are common to the relation that are involved in the Cartesian product, that is equated with the instructor ID, with the teacher's ID, teacher's table, instructor table. And natural join is a binary operation that allows us to combine certain selections and Cartesian product into one operation. And that is denoted, or it is denoted by the join symbol, that makes the Cartesian product of a two arguments, that performs a selection forcing equality on those attributes that appears in both the relation schemas, and finally removes the duplicate attributes. There are two types of relation that is consider instructor and the teachers. They compute in the instructor natural join teachers. So consider only those pairs of tuple where both the tuples from instructor and the tuple from teachers have the same value on the common attribute ID. So result is given within the expression that is given with the natural join, that is very complicated to perform. And since the schema for the instructor and the teachers have the attributes ID in common, so the natural join operation consider only the pair of tuples that have the same value on the ID. That combines with the pair of the tuples into a single tuple as the union of the two schemas. That is ID name, department name, salary, course ID. So it is using the two relations R and the S, which are of course list of attribute names. That is given to be the set rather than the list. We can denote those attribute name that appears in both R and the S. Let's start with the natural join of R and S. So this is the expression that is not with the natural join, that is denoted by the pi R union S, then sigma A1 S R1 A2 S2 R till till an and the R dot an and the S dot an. That means each and every element is multiplied by the or is natural joint or natural joint with the next expression. Please note that if R and S are the relation without any attributes in common, then R no, yes, R intersection S is not is null. So find the names of all the instructors in the computer science department together with the course title of the instructor that the instructor teach. So there is a pi, name, title, then sigma, department name equals to computer science, instructor teaches course. So the result relation for this query appears to be the combination of both the three tables, that is the instructor, teaches and the course, without inserting the parenthesis to specify the order in which the natural join operation on three relations should be executed. So in the preceding case, there are two possibilities. One is the instructor teaches, then course, then instructor teaches and the course. We did not specify which expression we intended before because the two are equivalent with each other. That is, the natural join is associative. The name, title, brand, game design, brand, image processing, cats, intro to the computer science, Srinivasan, introduction to the computer science, then robotics and database system objects. And it is also convenient at the times when we use the relational algebra expression by assigning the parts of it to the temporary relation variables. This is known as the assignment operation, that is denoted by the arrow, that works like an assignment in the programming language. So this is the example. R and S are multiplied with each other and stored in the temp1, and the output of this, that is a sigma temp1, is stored in the temp2. Result is combination of both the or union of both the relation, that is R and the S, in the temp2. So this evaluation of an assignment does not result in any relation being displayed to the user, but it is displayed with the multiplication. It is displayed with the expression to the right of the arrow that is assigned to the relational algebra or variable on the left of this one. That means whatever the expression that is given in the right, that is going into the left. The left is a variable that stores the output of the right hand side operators. So with this assignment operation, a query can be written as a sequential program consisting of a series of the assignments that is followed by an expression whose values are displayed as a result of the query. And for the relational algebra query, assignment must always be made to a temporary relation variable. And these assignments to the permanent relation constitute a database modification. And the assignment operation does not provide any additional power to the algebra. That is, however, a convenient way to express the complex queries. The next one is the outer join operation. That is an extension of the join operation to deal with the missing information. Suppose that there is some instructor who teaches no course. That means, null values are found out with the outer join. Very good. That works very similar to the natural join, but preserves those tuples that would be lost in a join by creating the tuples in the result containing the null values. So there are three types of forms of operation in the outer join. One is a left outer join, one is a right outer join, one is a full outer join. And all three forms of outer join computes the join and add the extra tuple to the result of join. Now when we talk about the left outer join, that takes all the tuples in the left relation that does not match or did not match with any tuple in the right relation. That means it pads with the null values if there is no output, if there is no values. Right outer join is symmetric with the left outer join, that is the same, but it carries on with the right side and it padded the nulls on the left side. Then full outer join, it does both the left and the right outer join operation, that padding the tuples on the left and did not match any from the right relation, as well as tuples from the right relation that does not match any from the left operation. That means it carries out or it makes a balance between the left and the right operation, or the left and the right outer join operation. And it's also interesting to note that the outer join operation can be expressed by the basic relational algebra operation For example, when I talk about the left outer join operation, that is written as R S union R minus pi RS null null. Next one is the extended relational algebra operations. What are the various extended form? So we now describe the relational algebra operations that provides the ability to write the queries that cannot be expressed using the basic relational algebra operations. These operations are known as extended relational algebra operations. First point is generalized projection. So first operation is the generalized projection operation that extends the projection operation by allowing the operations such as arithmetic and the string functions to be used in the projection list. What are the string operations? What are the arithmetic operations? Function that is used in the projection list. And a generalized projection operation has the following form. This is a pi f1 f2 till fn e, where e is any relational algebra expression that is denoted with the f1 f2 or any operation, and f1 f2 are the arithmetic expression that involves constant and the attributes in the schema of the e. And as a base case, the expression may be simply an attribute or a constant, and in general, an expression can use arithmetic operations such as the plus, minus, divide, multiply on the numeric value attributes, numeric constants, and on an expression that generates a numeric result. That also permits operations on other types of data also, that such as the concatenation of the strings. So this expression gives the ID, name, department name, and the monthly salary of each instructor. That is by ID, name, department name, salary divided by 12 instructors. So let's start with the extended relational algebra operation. First one is a generalized projection that extends the projection operation by allowing the operations such as the arithmetic and the string operation that we have done. Here f1 f2 till fn is an arithmetic operation that includes a constant also, attributes also, and d is any relational algebra expression. This is one of the example that you discussed, that is the find the ID, name, department name, and the monthly salary because it is divided by the 12. Then aggregation, that is aggregation operation G, which permits the use of aggregate functions such as the mean, average, or the set of the values. And these functions takes a collection of the values and return a single value as a result. So it takes out the multiple values and returns a single value as a result. For example, the aggregate function sum takes a collection of the values and returns the sum of all the values. Therefore, or thus, the function sum applied on the collection 113441 that returns the value as a 25, because 1 plus 1 is 2, 2 and 3 5, 5 9, 9 13, 13 and 11 is 24. So this uses the function aggregate function, that is AVG, that returns the average of the values also. So if I'm finding out the average, this is 24 divided by 6, very good, because there are total 6 elements, that gives output as a 4. And the aggregate function count returns the number of the elements in the collection and returns 6 on the preceding collection. Other common aggregate functions includes min and the max, that returns the minimum value and the maximum value in the collection. Whatever the maximum value, minimum value, they return. So if I'm talking about the minimum value, that means lowest value, that is 1, and if I'm talking about the maximum value, that gives the output as a 11. And the collections on which aggregate functions operate can have a multiple occurrence of the value. The order in which the values appears is not relevant, and such collections are known as the multisets. And sets are a special set of multisets where there is only one copy of each element. So to illustrate the concept of aggregations, we shall use the instructor relation. So suppose we want to find out the sum of all the salaries, the relational algebra for this expression is sum salary instructor. And this G is a calligraphic font that is read as the calligraphic G. And the relational algebra operation G signifies the aggregation that is to be applied, and it is a subscript that specifies the aggregate operation to be applied. Whatever the aggregate operation that is applied over here, that gives the output as a containing a single row with a numeric value that corresponds to the sum of the salaries of all the instructors. And there are multiple cases in which we have to eliminate the multiple occurrences of the value. So in that case, we use a distinct that can be applied at the end of the function name. Now, listen carefully. This is my query to each and every one. Find the total number of instructors. Total number of instructors who teaches a course in spring 2010 semester. So I've given a condition that is spring 2010 semester, and I've also given a field name that is a course. In this case, an instructor counts only once regardless of the number of course section that the instructor teaches. So this required information is contained in the relation teaches, and we write this query as follows. So G count distinct ID, semester equals to spring and year equals to 2010 teaches. This aggregate function count distinct ensures that even if an instructor teaches more than one course, she is counted only once in the result. And there are multiple circumstances where we would like to apply the aggregate function not to a single set of tuples, but instead of a group or instead to a group of set of tuples. As an illustration, consider the query, find the average salary in each department. So write the query as a department name, G average salary instructors. So that shows the tuples in the relation or instructor relation that is grouped by the department name attribute. And this is the first step in computing the query result. This specified or the specified aggregate is computed for each and every group that is the result of the query. So this is the one of the tuples of the instructor relation that is grouped by the department name attribute. There's the ID, name, department name, salary. ID is 76766, name is Quick, department name is Biology, and the salary is 72,000. So these are the tuples that constitute the query as a find the salary or average salary of all the instructors. We write the query as follows, that is the average salary instructor. And in this case, the attribute department name omitted from the left hand side of the G operators on the entire relation is treated as a single group. This is the department name, salary, biology 72,000, computer science 77333, electric engineering 80,000, finance 85, history 61, music 40, physics 91. This expression is used to find the average salary in each department. This is known as a multi-set relational algebra. So unlike the relational algebra, SQL also allows the multiple copies of a tuple in an output or input relation as well as in the query result. That gives the output as a multi-set output. Yeah, multi-set output means that is used with the aggregate function that is used as a common function. For example, if I'm talking about tuples in a group that have a same group, that have a same value for G1, G2 till Gn. Then tuples in different group that have different values for G1, G2 till Gn. In the same way, groups can be identified by the value of attributes C1, G2, Gn that have a result that have a tuple where IA the result of applying aggregate function Fi on the multiset values attribute in the group. That is combined with the set of the groups that is combined with all the